What came first? The Norbert or the egg?
Welcome to level 2, Scout. You know what level 2 is like? Level 2 is like the final rays of sunlight on a summer evening before you're enveloped in the stormy darkness that is level 3. Tonight, you'll be modding the VEX IQ Flex into Norbert. Things will heat up in the Fusion Kitchen as you virtually add the finishing touches to your build.
You will battle it out in the one, the only Dragon Egg Rescue Battle.
Perhaps most excitingly, you'll be diving into a completely new world on the coding front.
It's called RobotC.
You're done with ModKit in the land of blocks. It's time for raw, real, text-based coding. This robot definitely ranks code heavy.
This video is brought to you by Egg. Go to egg.com/nerdygirls to get an egg. Next.
All right, if you're starting with a fresh kit, easy peasy. Just follow the Flex build PDF instructions to the bitter end. And if you're starting with Poe from level 1, easier peasier. You're just gonna back up your build to look like the end of step 45 in the Flex build PDF and build on from there. Or you can follow along here. And let's start things off with mounting the touch LED. So you're gonna grab a 2x2 corner connector, 4 1x1 connector pins, your touch LED sensor, and a cable. You're gonna mount that sucker on the back of Norbert like this. It might even already be there, in which case you just got pranked. And finally, the Dragon mod. Mount your 3D printed dragon wings of choice. Link in the description to the OG creator of this dragon wing design and the file to print your own dragon wings. CAD time. You're gonna click the link in the dink, come back hink when you're dink. Goodbye.
Hi pal, and welcome to Coding with your bud, Greta. Today we'll be plunging into the wonderful land of RobotC coding. You will walk away feeling significantly less noobish than you did when you walked in that door. Let's begin by opening up RobotC. First, we'll make sure that everything is configured to work with our old friend, the VEX IQ. Make sure that platform type is set to VEX IQ, and let's go ahead and make sure VEX IQ controller mode is set to Teleup, since we'll be using the controller for Norbert. Create a new file and name it whatever you like. And you might notice that we automatically have this task main thing in our code file. This is our main function, the command center for our code. It's basically just telling RobotC, hey, when you run this code, execute all that we put in here between this top curly brace and this bottom curly brace. So the next step is to set up our motors. In RobotC, there's this handy little tool called motor and sensor setup. For Norbert, let's make sure we're on the motors tab to set everything up. I'm gonna call my drivetrain motors left motor and right motor and type those names into ports 1 and 12. And name my arm motor, and I'll go ahead and type that into port 10. You can name them whatever you want. Go wild. By the way, see how the first letter of the first word of the motor name is lowercase and then the first letter of the second word is uppercase? You'll see that style of naming a lot, and just know know that it's the standard way of naming motors and variables and functions in RobotC. It's called camel case. Make sure all motors are configured as VEX IQ motors. We're going to reverse the left drivetrain motor, meaning whenever we tell it to go forward, it'll actually go backwards. That might seem weird AF at first. I'm in the same boat. In RobotC, making the motor spin forwards translates to our wheels spinning clockwise. Now, clockwise for the right wheel makes it spin forward, so we're good. But if you turn the robot around and look at the other wheels, you'll see that clockwise actually makes them spin backwards. So by reversing the direction of the left motor, we're essentially telling the brain that when it receives the command to go forwards, it should turn the left wheels counterclockwise and not clockwise. Finally, we gotta set up our touch LED under devices. We know it's plugged into port 9, and we can use the camel case style of naming when we name it. How fun! Just tell RobotC that we're dealing with a touch LED, then hit apply and OK. And boom! Some code is magically generated up here that will provide to RobotC all of the information we just inputted. Things like motor ports, names, which ones are reversed, all that fun stuff. Let's test our drivetrain motors real quick to make sure that we're actually going forward. In RobotC, there are a few more steps to this than there are in ModKit. But let's jump in. Let's step inside our main function. And because the code we're about to type is inside the main function, it's easier to read if you indent the cursor instead of typing your commands back here. To make our drivetrain go forward, we have to provide power to both the left motor and the right motor. The command to do that is set motor speed parentheses semicolon. And in RobotC, along with tons of other programming languages, you end every command with a semicolon. Inside this command, we're going to give it two things. The name of the motor we're giving the power to, I'm doing the left motor, and the amount of power. In RobotC, you can give power anywhere in the range of negative 100, which is full speed backward, to positive 100, which is full speed forward, with 0 being no power. I'll give you about 60, but you can do whatever you want. And make sure that the name of your motor and the motor power is separated by a comma. To give power to the right motor, we can copy, Control-C, and paste, Control-B, this line, and then change left motor to right motor. So now we have the motors running, but we don't want them to run forever. We want them to run for a certain amount of time and then stop. So let's make the code wait with the command wait 1 sec, parentheses semicolon, and enter the number of milliseconds we want to pass before we move on in the code. I'll say 1 second, which translates to 1,000 milliseconds. Finally, after the 1 second has passed, we need to turn off power to the motors. That's easy enough. Let's just copy these two set motor speed commands up here, paste them after the wait command, but change the power to 0. Let's save it and then compile it. It will tell us if there are any errors or bugs in our code. And to test it, let's plug in our bot, turn it on, and plug in our powered on controller since this is downloading as a teleop file. And in order to make RobotC code download onto a VEX IQ brain, we need to download something called firmware onto the brain. This only needs to happen once, and then you should be all set for about a fortnight or two. Click on Robot, then download firmware, then standard file. It should only take a few seconds to download the firmware. And that's what I would call a yeehaw moment. Finally, hit download to robot. Wait for the pop-up, and then you're good to go. Set the robot down, navigate to teleop code, and our file should download there. How crazy is that? Sweet deal, now let's get back to the workbench. If you wanted Norbert to go backwards, you could change both of these powers to a negative. If you needed Norbert to turn, simply make one of those powers negative. Left power negative for a left turn, and right power negative for a right turn. So the Dragon Egg rescue battle is a little different from the battles of level 1, which generally had two parts, autonomous mode and teleop mode. This battle is teleop only, which means that Norbert will be controlled by the driver for the whole match, baby. There is something different about this battle, because we'll be adding something very special to our code. Macros. So generally speaking, a macro is something that can be broken up into a bunch of super fun little steps. So let's think about a battle. One thing the robot has to do is pick up a chalice with a rare dragon egg inside of it. Even though this one thing seems simple, it can actually be broken down into a few steps. You gotta go forward, lift up, and then maybe back up to position yourself for a smooth delivery. Instead of doing all of that manually when we see a chalice, what if at the push of a button, all of the steps could execute automatically? Let's get back to the code. So we don't need this code snippet, so we could just delete it. But just in case we need to reference it, I'm gonna comment it out so that's still there, but just hidden from RobotC and won't run unless I uncomment it. Since this code spans more than a single line, we need to do a multi-line comment, which is / where we want the comment to start, and then * where we want it to end. Boom, now it won't run. Life hack. By the way, if you want to comment out a single line, just do the old double slash. In fact, you should add a comment at the top to leave your mark on this here file. The first thing that we're going to put in our main function here is a loop that repeats forever. To do that, type repeat and then parentheses forever, and add an opening curly brace and a closing curly brace. So when we run our code, the first thing we encounter is this forever loop. We enter the loop and repeat whatever commands we cram between this opening curly brace and this closing curly brace over and over again. So first, Let's get our robot drivable, shall we? If you recall, there are two main ways of controlling your drivetrain. Arcade drive, where one joystick steers the whole robot, and tank drive, where the left joystick controls the left side and the right joystick controls the right side. I'll show you how to do tank drive first, and the way this works may make zero or possibly negative sense at first, but it's fine, you'll get used to it. So the axes for each joystick are lettered. The vertical or y-axis on the right joystick is called channel D. For the left joystick, it's channel A. The horizontal or x-axis on the right joystick is called channel C, and on the left, it's channel B. You can think of the channels like a graph. Each channel has a range from negative 100, which is full power backward, to positive 100, which is full power forward, and you guessed it, the middle is 0, just like motor power. The commands for this are going to start exactly like when you'd normally give the motor a power, so let's set up two set motor speed commands, one for the left motor and one for the right motor. Except in this case, the amount of power it gets depends on where the joystick is, vertically speaking, at any given time. So instead of giving the motors a number for power, we're going to tell them, hey, the power depends on where the joystick is. We can find out where the joystick is using getJoystickValue parentheses. Now we just need to tell this command which channel we care about. The left motor cares deeply about channel A, while the right motor only has eyes for channel D. And because these commands are inside the forever loop, the motor power will constantly get updated to match where the joystick is at. And let's just leave a comment to ourselves so that we remember that these commands are for tank drive. Now let's do arcade drive. I'll copy tank drive and then comment it out, then we can paste it and delete the channels. To achieve arcade drive, we're going to make the power the value of the vertical channel. I'm using the left joystick, so channel A, but if you're using the right joystick, use channel D, plus for the left, minus for the right, the value of the horizontal channel, channel B for me. Finally, we're going to add an extra set of parentheses around the two commands and divide the result by 2. So basically, the power going to the left motor is equal to taking the value on the y-axis, adding the x-axis value, and halving it. Same for the right motor, except we're subtracting the x value. It'll sink in over time, like, say, a person trapped in quicksand. For now, just comment it as arcade drive and tuck it away. Congration, you done it! And since this stuff is inside our forever loop, let's make sure it's readable by indenting it a little. Okay, so now let's set ourselves up to be able to control the arm with the controller. We want the arm to move up if one button is pressed, down if another button is pressed, and hold still if no buttons are pressed. So let's translate that into some sick AF code. So there are 3 things we want to check for if one button is pressed, if another button is pressed, and if no buttons are pressed. You can see we're using an if statement up here, then an else if statement, and then an else statement. Starting with the if, let's pick a button to control the lifting of the arm. I'll do the upper right bumper, aka button R up. So the way we check if it's pressed is we say if the value of button R up is equal to 1. We check the value using getJoystickValue of button R up, and to check if it equals 1, we do equals 1. So if it's pressed, it's true, it's a 1. Otherwise, it's not pressed, it's false, it's a 0. So if this button is pressed, RobotC will execute whatever's in between these two curly braces. And what we want to do is give the arm motor a positive power. Okay, now we're all set on that. If R up isn't pressed, RobotC then moves on and checks the next one, the else if. We'll use this one to check if the button to lower the arm is pressed. I'll do the lower R bumper. So if it is pressed and equals 1, we'll copy and paste our arm motor power, except we need the power to be negative because we're lowering the arm. Finally, in the case that neither button is pressed, RobotC will execute whatever's in the else. In this case, we'll turn off power to the arm motor. Alrighty, I'm gonna leave some comments so that we remember what this code is in charge of doing. Save it, compile it. I'm gonna test my code out to make sure the basic teleop is working before we move on. Click download to robot and watch the magic happen. And now you can unplug the bot and test to your heart's content. Now let's design a macro to automate the picking up of our chalices during the battle. So there are basically 5 steps. Turn on the touch LED to notify us that the macro has been activated. Go forward to catch the chalice. Lift the chalice up, go backwards to prepare for delivery, and turn the touch LED off to tell us that the macro is over. All of that can happen at the gentle touch of button E up, or whatever button you want to use. Let's start by adding another else if right in here to check if button E up is pressed. We could just write the commands for the macro directly in here, but that would take up a lot of lines and it's a little bit too messy for me. Let's store all the commands for our macro in a secret box, and activate that secret little box when button E up is pressed. That's right. We're making a function for all your secret box needs, TM. Here are the steps to constructing your very own function in RobotC. First, we gotta warn RobotC that we're gonna be using a function in the program. So up before our main function even kicks off here, we're gonna type void. Don't worry about the significance of that right now, we'll explain it later on. Then the name of your function, followed by a parentheses and a semicolon. Notice how I use camel case for the name? Yeah, you do. This is called a forward declaration. Again, giving RobotC a heads up that there's a function living in this here program. Now let's actually build out this function. We're gonna have to go deep down to the depths of our code here. And outside the main function is where we're gonna build this function, the secret box to hold our precious little macro. Down here, we're gonna type void, our function name, parentheses, then an opening curly brace and a closing curly brace to give a definite starting and ending point to our function. So the first thing in the macro is that we want the touch LED to light up to let us know that it's macro time, baby. The command for that is set touch LED color, and we have to give it two things, the name of our touch LED sensor and what color. I want to do green, so I'm going to type color green, semicolon, boom. So now we want the robot to go forward, and we're used to this by now. We're going to give power to both the left and right motors, wait for a certain number of milliseconds, I'll do 700, and then turn off power. Then I'll add in a teeny little wait command just to space out the steps. You can experiment with how long you want to lift the arm. I landed on around 1600 milliseconds. Then turn off arm power. A teeny little wait to space out commands. Then we want to back up, which is just like going forward up here, but with negative motor power. So cool. And since we have now completed our macro, let's turn the touch LED off using this command. So we got our macro stored inside our function here, but as of right now, this function will never be activated and run the macro commands. That's because we haven't called it from our main function. RobotC will just ignore our precious little macro function unless at some point in the main function we tell it to activate the macro function. Just like in ModKit, the only time we want this function to activate is if button E up is pressed. So back here, if E up is pressed, we're going to call our function by typing the name of the function, no void, just the name, and then parentheses semicolon. Function calling all over the place. So if you can imagine, RobotC is constantly checking over and over again to see if any buttons are pressed. All of a sudden, E up is pressed, so RobotC goes inside here, sees that we're calling our function, so then it jumps down to our function, executes the commands, then when it's run all of the commands inside the function, it pops back up to the main function where it left off and keeps going on its merry little way, checking for buttons. That's the life. There's one more macro we need, and that's liftoff for the end of the battle. So let's do it all over again, baby! First, let's add in one last else if in our main function. If, let's say, button F down is pressed, we'll come back to this in a second. First, we need to define a new function to store this macro. So step one, forward declaration up here at the top, and let's give it a name. Now all the way down after our pickup function, we'll build out, aka define, our liftoff function. Void liftoff parentheses, opening curly, closing curly. Now we can put the commands for a macro that will automate climbing in the battle. First, to notify the driver that this macro is running, let's use this command to turn our touch LED a beautiful shade of blue. We'll give the name of our touch LED and color blue. Tiny little wait to space out command. Assuming that Norbert is approaching the bar with its arm up, we want Norbert to back up into the bar, so we'll have it back up a little bit. Tiny wait, then we want to hook onto the bar, so we'll have Norbert lower its arm a little bit. Tiny wait. Finally, it's time for liftoff, so let's have that arm motor lower all the way. You can experiment with this number. And by default, RobotC has the motors hold their position against gravity. Now all we gotta do is call this function when the F down button is pressed. We did it! Save, compile, fix any errors you might get. We're here, baby! Now I just want to touch on a couple little housekeeping things for this code file before we start testing and tweaking those nums. First thing, one way that you'll see code commonly structured is to put opening curly braces on the same line as the function headers or the if, else if, and else statements. So we can do that real quick. Also, the else ifs and elses will often go on the same line as the closing curly brace of the previous if or else if statement, like this. So notice how in our functions down here, we're using the same motor power of 60 over and over and over again. And let's say that for whatever reason, we need to use 80% power instead of 60 across the board. Well, we'd have to go through and change each of those little nums. So instead, at the top of the program, we're going to do something to simplify this. Let's create something called a variable, which is essentially a little storage container for different types of data. Let's create a variable to store motor power that we can use across the board. There are a lot of different types of variables. I'm going to use type int, which is short for integer, which is a whole number. Space. Now we type what we want to name our variable. I'll call mine motor power. Finally, we have to assign a whole number to motor power for it to store. We're going to assign it 60 with equal sign, semicolon. Now back down here, we can replace each of our 60s with our variable named motor power, which right now is storing 60. Just keep the minus sign in front of it if it's negative. Now, if we decide that we don't like 60% motor power, we just go back up to the top, change one number, the number that motor power is storing, and all of these powers will update to match what motor power is now storing. I change it to 80 up here, all of these down here are now 80. All right. Save, compile, download, test, tweak the numbers until you're happy with how the robot moves and how the macros work, and you're ready for battle. Oh my god, that was so much. P.S. Think about the fact that you just wrote over 100 lines of text-based code.
Welcome to the Dragon Egg Rescue Battle. Now, here's the situation. Your precious dragon eggs are stowed in chalices located around the battle arena, and you must return them to the nest. But oh no! The nest can only fit 3 chalices. Chali? You must grab the final golden egg chalice and bring it with you as you take flight. Eggs can only be picked up, and you can only take flight using the macros that you coded. You have 2 minutes.
Yeah, it was the shark, and his hand is missing, but the 2 pilots are Joseph and Tyrone. Yeah, it was the shark, and his hand is missing, but the 2 pilots are Joseph and Tyrone. Yeah, it was the shark, and his hand is missing, but the 2 pilots are Joseph and Tyrone. Yeah, it was the shark, and his hand is missing, but the 2 pilots are Joseph and Tyrone. Yeah, it was the shark, and his hand is missing, but the 2 pilots are Joseph and Tyrone. Yeah, it was the shark, and his hand is missing, but the 2 pilots are Joseph and Tyrone.